Good afternoon. If you haven't been here before, welcome to the Inamori International Center for Ethics and Excellence. I'm Barbara Snyder, president of Case Western Reserve, and I'm so pleased to have you all here with us to celebrate the creation of the Thomas W. and Nancy P. Seitz Professorship in Advanced Materials and Energy, and of course the appointment to that position of our faculty member, Ica Manas Zloczower. Of course, we know Professor Manas as Professor Manas. Endowed chairs are truly meaningful gifts, and I want to say to Tom and Nancy, these are the things that allow us to recognize the very best of the best among our faculty, and it is such a meaningful gift. They allow us to recruit and retain people like Professor Manas, who are making such a tremendous difference here, helping our students, and they are actually the first beneficiaries of every endowed faculty position that we get. The students are the ones who engage with our faculty members in the classroom and in the lab. But in this case, actually, this gift will also benefit patients down the road, the environment someday. So the work that Professor Manas is doing is really making a difference in a lot of areas. So we're really pleased to be able to have this. This Seitz gift also supports the Institute for Advanced Materials, one of the signature programs at Case Western Reserve, and it is working to advance the next generation of materials for healthy and sustainable living. Projects range from improved biomedical implants that meld with the body's own tissue to coatings that protect offshore wind turbines from wind, water, and sun damage. And the Institute actually engages more than 100 faculty members from our medical school, our dental school, our engineering school, and from the College of Arts and Sciences, all working together to solve challenges and seize opportunities in their collective fields. So the Seitz gift truly does speak to the impact that donors have on our university and literally on the world as this work goes forward. Tom and Nancy Seitz are longtime supporters of Case Western Reserve. Tom is a graduate. He's got his undergraduate degree from the Case Institute of Technology. I won't say when. And he's a key volunteer on a number of committees at the Case School of Engineering. He also co-chairs Case Western Reserve's Corporate Visiting Committee, which is a group of successful business leaders who share their insights to help the university. Tom praises the superb technical education he received here, but also says the university imparted something more, and I'm quoting from Tom now. Learning how to learn and developing problem-solving skills made me a lifelong student. Tom, that's our goal with every student who comes through our doors. And Tom, of course, truly is a lifelong learner. After graduating from the Case Institute of Technology, he went on to earn his MBA from the University of Chicago and joined the Sherwin-Williams Company in 1970. He's had a variety of leadership roles in technical, engineering, manufacturing, logistics, and general management areas, and was named Senior Vice President for Strategic Initiatives in 2007. Nancy has been equally active professionally. She worked in retail design in Chicago, Dallas, and Atlanta before moving back to Cleveland, where she joined the Cleveland Museum of Art and eventually managed the institution's special events and food service. She now is focusing her energy on a variety of volunteer activities and serves on the board of Laurel School, the Cleveland Restoration Society, the North Union Farmers Market, and the U.S. Women's Curling Association, where she is a past president. I want you to know that both Tom and Nancy are involved in the sport of curling. And I think Tom was once referred to as Prince of the Pond, if I'm not mistaken, for his pivotal role in assisting with ice at an event. All the things that we find out, Tom, when we do our research. Yes, literally. So sometime I would love to see both of you when you're curling. I look forward to that day. I want to ask Tom and Nancy to join me up here because we have a tradition at Case Western Reserve. So come up. We have a gift for you. When you give us a chair, we give you something that we hope you will enjoy, and the something that we give you is right here.
Of course. How appropriate.
So it is a chair, and we hope that this will cause you to remember the impact that you are still having every day on our campus with this gift. So I'd like to invite either or both of you to say a few words.
I'll let you speak.
Well, I'll make this short and sweet. I first would like to issue some thank yous. I'd like to thank Nancy and my family for supporting me in my career at Sherwin-Williams. Without them, I would not be in a position today to give this kind of a gift back to Case. Also, I have my cousin Glenn and his wife sitting here in front of me. Glenn is 10 years older than me, almost to the day, and went to Case exactly 10 years before me. And he was sort of my childhood hero growing up, and I always wanted to be an engineer like Glenn, so that's why I came to Case. So if it weren't for him, I wouldn't have come here, and we wouldn't be here today. And there's a number of my colleagues from Sherwin-Williams here, and those of you that are from Cleveland know that Sherwin-Williams is a great Cleveland company. They've been here since 1866. We're looking forward to our anniversary here in 2016. And again, without the Sherwin-Williams Company and the now some 35,000 employees that have helped make that company what it is, and the opportunities that I got working for Sherwin-Williams, again, I wouldn't be able to do this for Case. So I want to thank the Sherwin-Williams family for all they've done for me. Why Case? I think Barbara said it well. A lot of who I am today is because of my education at Case. I suspect that's true, I hope, for every undergraduate, but at least for most of them, I'm sure it's true. And I did learn how to learn. I've been a lifelong learner. It's kind of what I like to do. And problem-solving skills that I learned here have done very well for me over the years. I haven't done any true engineering, I must confess, for probably 15 years. But the same skills, the analytical skills, problem-solving skills, I continue to use going forward. So I'm very pleased, along with Nancy, to make this gift to the school. You're on a roll here. The last several years have been great for the school. We have a record incoming freshman class, a record number of students coming into the to the School of Engineering. So things are working well, and we're very pleased to lend our support to the school.
Thank you. Thank you, Tom. Thank you. Thank you. That doesn't mean she doesn't get to take the chair. We just pack it up. We pack it up nicely later. So Tom and Nancy, it is really our honor to be able to celebrate with you today, and we are so grateful again for all of your support over many years, and especially, of course, for this gift that we celebrate today. Now it is my great pleasure to introduce another one of our stars at Case Western Reserve, Don Feek, Vice Provost for Undergraduate Education and Professor in the Department of Chemical Engineering in the Case School of Engineering, who will introduce Professor Manas. Don is a great person to work with. He's a wonderful colleague in Delbert Hall. We are really lucky to have him on our campus. He served in a variety of leadership roles. I know him best as our vice provost, but he is a terrific leader, and I introduce him to all of you to introduce Professor Manas.
Thanks, Barbara, very much. It is my true honor to provide a few introductory remarks about Professor Manas, whose accomplishments we are recognizing and celebrating today. Before I do that, I probably should try to explain why Ica gave me this opportunity to introduce her. I met Ica very shortly after she arrived at Case Western Reserve University. Both Ica and I immediately recognized that we had complementary backgrounds that intersected in similar research interests, and that we both had matching outlooks on our roles as faculty members and as mentors to students. This was a very natural start of an active and fruitful collaboration that I've been enjoying for more than a quarter of a century. I should comment that Ica arrived as a precocious teenager. When Ica asked me to introduce her at this ceremony, the first question that popped into my mind was, which of her outstanding qualities should I try to emphasize? The list of Ica's accomplishments in research, teaching, and leadership, both inside and outside the university, is lengthy and impressive. As you may know, Ica is the current president of the International Polymer Processing Society, which is recognized as the world's leading technical organization in the field of polymer processing. We have received a letter of congratulations from the executive committee of the Polymer Processing Society, which they have requested to be read at this ceremony. It's a long letter. Reading the whole letter would take more time than I've been allocated, but please let me read a few excerpts because they nicely summarize her research and teaching accomplishments. So again, from the letter. We would like to express our joy and congratulate our colleague for this high achievement that highlights her talents in research and education. Professor Manas is one of the worldwide leaders in the polymer and polymer processing fields, with crucial and seminal contributions in various fields at the interface between chemistry, mechanics, and technology, including mixing and compounding, dispersion, rheology, polymeric multiphase systems, processing and design, and optimization of mixing and turbine tools. Her work, both experimental and theoretical, on dispersion of agglomerates and clusters was a breakthrough in the field and is widely used both in academia and industry. Her book on mixing and compounding of polymers was a bestseller in its first edition in 1994, and its 2009 edition has received the same success and enthusiasm from the international scientific community. Professor Manas is the first woman to take the presidency of our society, and with her enthusiasm, professionalism, and human values, she is running the society in a superb and proactive manner, and we are very thankful for her strong involvement, dedication, and professionalism. Professor Manas has received various awards and honors, and recently she was awarded the 2012 George S. Whitby Award for Distinguished Teaching and Research given by the American Chemical Society Rubber Division. Professor Manas is also the editor-in-chief of the Journal of Polymer Engineering and serves on the advisory board for the publisher Hanser. She has an impressive track record in terms of scientific dissemination and supervision of highly qualified personnel, but most importantly is the international recognition of her scientific leadership, as it can be judged from the incredible number of invited keynote and plenary lectures in international meetings and congresses. She's a talented and an outstanding scientific speaker, able to present complex science and technology concepts in a very clear way that makes everyone understand even the complex math behind the concepts. Professor Manas expresses the joy to convey and transmit what she knows not only to highly achieved scientists, researchers, and engineers, but also to students and alumni. So it's very clear that Ica's scientifically accomplished. But I thought it would also be important for me to try to provide some insight on who Ica is. She really values people. She takes to heart her role and responsibility as a mentor. Because I worked very closely with her, it's very easy for me to see Ica's impact on her students. She works diligently and strategically to make sure that each of her students is developed to her or his full potential. To gauge the magnitude of Ica's impact on them, I contacted some of her former research students and invited them to send me any comments they would like about her. They did respond, and a clear pattern developed. Let me give you a sampling of some of their comments. Maybe you can hear the pattern. From one student, from my very first encounter with her, I understood that Dr. Manas would not just be engaged in my academic growth, but she would be my mentor overall. Dr. Manas provided me with just the right balance of coaching and guidance while still granting me enough freedom so that I could become independent and develop my self-confidence. Another student writes, she took care of all her students, from their research success to looking out for their family members. Still another student writes, she cared about my personal growth and guided me along my career path. I really appreciate having been her student. Another student, the many lessons learned from Professor Manas will serve me throughout my life, both professionally and personally. For this, I will be forever indebted to her. Professor Manas did not want me to give up. This was a precious present for me. Another student, What I discovered of Professor Manas was there are two parallel aspects to being her student. One is the technical learning, including research, presentation skills, paper writing, etc., while the other is more focused on professional values and growth. And this latter element is the more precious one. Lastly, Professor Manas has fully understood and taken upon herself the responsibility to mentor PhD students, where the education does not only mean papers and books, but it is also education for the professional life we have ahead of us. By doing so, she gives us a huge and priceless gift. A gift indeed, one befitting the recognition that is accompanying the Seitz chair. Please help me welcome Ica to the stage.
Wow. Well, Don, first of all, I really would like to thank you very much for your kind words and for the extraordinary introduction. It's highly appreciated. And not only the introduction, but I really value the friendship and the guidance I get from you over the years. So thank you. So I was asked to give a talk about my research field, and this is a difficult one. So if it's not perfect, I hope you will understand why. First of all, I would like to say that I'm truly indebted to the Seitz family for the very generous gift and the fact that they allowed me to get honored today. Really thank you from the bottom of my heart. I also would like to say that I met Tom many years ago. I met Nancy only this summer, but I was really impressed over the years and this summer by the very unassumed demeanor of both members of Seitz family, and the fact that they truly encourage the advancement of people. The fact that they are very much concerned about increasing the number of women in science and technology. And this is really very dear to me. I hope that with this endowed chair, I'll be able to do more research and more advancement in science and technology, and to live up to the traits of your wonderful family. So thank you from the bottom of my heart. So as I mentioned before, I'm supposed to talk about my research. And so my research is really in the area of mixing. The definition, it's a common operation intended to reduce system non-uniformity. And where can we find mixing? Well, certainly, if you look in a bowl of grains, you can see mixing of the cereals. You can see mixing of paints in wonderful paintings. Here is an example of stretching and folding some viscous fluids. But also, if you think about the clouds, that's also a mixing process. The first one is, the previous one was laminar, this one is turbulent. And certainly, we encounter mixing in everyday life when we prepare our food. Now, going for the equipment which we use in mixing, we start with a mortar and pestle, and we go on to brushes, which were used over the years by very famous painters and by not so famous painters today, perhaps. We also see mixing in processing equipment, such as the bamboo mixer or the single-screw extruder. And more recently, we see mixing in very small devices, which are those mini mixers. So the question is mixing an art or is it science? So I searched the literature, and this is what I came up with. Well, it's probably a trade, and it was used, by ancient people and more modern people. It's also an art of how to make a good drink. Now, of course, if you would ask me, I will tell you that mixing is science. And this is the book which can prove it. So, since I cannot talk about all aspects of mixing, I decided to choose just a few. So today I'm going to focus on mixing of fine particles in material processing. And so where do we see that? We see it in coatings which are resistant to various things. We see that in additives, which we are using for rheology control. Well, I want you to look at this, okay? We see that also in the paints made by Sherwin-Williams. We see it in manufacturing of tires, and we see it in building the yachts, which we hope one day we'll enjoy. So let's talk about mixing of fine particles. So there are actually two mechanisms which are important in mixing. One is the dispersive mixing, which means the breakup of the large clusters into smaller ones. And the other one, it's called distributive mixing, which deals with the spatial distribution of the minor component into the system. And so really the goal is to achieve particles of reduced size well distributed in the entire system. And so just for the definition, the dispersive mixing is the breakup of the minor component along the process streams, and that can happen in an extruder, in a mixer, in a roll mill, and even in a sonicator. But if we think about what do we want to achieve, we want to go from an agglomerate, which is a cluster of particles, down to the individual components, which can be either the very fine particles, the primary one, but also sometimes only to the aggregate level. And so if you think about what is happening in the mixing process, actually it's a balance of forces between the cohesive forces and the hydrodynamic forces. And the cohesive forces are the one responsible for holding those particles together, whereas the hydrodynamic forces are the ones created in a flow field and trying to disperse, in which we try to disperse an agglomerate. Talking about an agglomerate, one has to realize that the agglomerate actually has a hierarchical structure. So it's formed from primary particles, usually in the length scale of 10 nanometers, aggregated into aggregates, which again have one order of magnitude, perhaps larger size, and those cluster together to form the agglomerate. And so the idea is to apply hydrodynamic forces which will be big enough to overcome those cohesive forces. And if that is the case, the mechanisms for breaking those agglomerates can be simply erosion, which is just the detachment of fine particles from the outer surface of the agglomerate, but it also can be rupture or even shattering of the agglomerate. No, but the story is not actually that simple. And the reason is that we can control dispersion by affecting the flow field characteristics. So we talk about the strengths of the flow field or the characteristics of the flow field. And we can certainly affect the cohesive forces by the morphology of the particles. So here we talked about the density, the structure, the surface area, the morphology, or the surface treatment of those particles. But if you think about the fact that the agglomerate is a porous object, the fact that you put it into a flow field, there is fluid infiltration inside the agglomerate, and that actually will affect both the filler cohesivity as well as the way in which the stresses are transmitted to the agglomerate. And so I sought to show you just 2 examples of how this process of infiltration actually will give different mechanisms of dispersion of agglomerates. So first of all, let me say that if you have just a dry agglomerate, so let's assume that we put the agglomerate really immediately into the flow field, and there is no or very little infiltration of the matrix, obviously the agglomerates will disperse at the level of stress similar to their tensile strengths. And so here is an example where we compare 2 different agglomerates of different tensile strengths under the same hydrodynamic forces applied, and obviously the one which is less cohesive will disperse more. And so in fact, if you want to picture what is happening there, it is the breaking of the physical structure of the agglomerate by the application of the hydrodynamic forces. Now, if you put this agglomerate into a fluid, then you will have some fluid penetration inside the agglomerate. Remember, that's a porous structure. And so what happens is that as the agglomerate is soaking more and more into the matrix, there will be a change in the cohesivity of that agglomerate. And you can picture it like having a dry core, which is not yet infiltrated, and a shell, which is infiltrated by the fluid. And we have done some predictive work how to calculate the thickness of the infiltrated layer. So let me show you the following. If we take calcium carbonate, and you are all probably familiar with calcium carbonate, and you make those agglomerates soak in the fluid, what will happen is that as you increase the level of infiltration, that leads to a decrease in the level of dispersion. So agglomerates which were soaked for 10 minutes only will disperse more than the ones which soak for 25 minutes. So the reason for that is, if you think in terms of the infiltrated agglomerates, what happened is that this fluid which penetrates inside the agglomerate creates some liquid bridges between the particles, and that will enhance the cohesivity of the agglomerate. Consequently, it will disperse less. However, we did some interesting experiments using silica, and we actually soaked the silica agglomerates into the fluid for different amounts of time, such that the level of infiltration increases with time. And what we saw is that actually, as you increase the level of infiltration, you increase also the level of dispersion. That's totally contradictory to what we have seen before. And so, in a sense, what happens is, so we were not sure, well, maybe the student made a mistake, maybe there is something funny there. No, there is nothing funny there. Actually, that's exactly the case. So then we said, okay, let's see if we can make sense out of this data. So here is a plot of the level of erosion of those agglomerates as compared to what we calculated to be the level of infiltration of the agglomerates using our model, our predictive model. And so what we saw is that the level of infiltration corresponds exactly to the level of dispersion. Now, that's interesting. And why is that interesting? Because it seems that the more you infiltrate, the more you disperse. And so what comes to mind is the fact that actually you peel off the infiltrated layer from the dry core. And that's a totally different mechanism of dispersion. That's called an adhesive failure. So the first one which we saw with the calcium carbonate was a cohesive layer, where you have to break down the structure of the agglomerate. Here in the adhesive layer, imagine like an onion, which you peel. So that's exactly what you do here. You peel off the infiltrated layer from the dry core. And that's very interesting. So and we have a theory about why is that happening, but I'm not going to tell you all the secrets. The only thing which I would like to point out is that in that, the mechanism, the physical mechanism there, is that when you infiltrate that agglomerate, what happens is that you sort of pull together this infiltrated layer and make it strong. It's like a strong shell, but you pull it apart from the dry core. And so at the interface between the wet and the dry, there is a weak point where the agglomerate will break. And that's the reason why you have that adhesive mechanism of Fair. So it's the wet-dry interface where you have that weak point where actually erosion will occur. Okay, so that's about mechanisms. Let's talk a little bit about equipment. Now, we did not model, actually, how you use a pestle and mortar to mix the grains, but we saw that more relevant will be to model equipment which is used in polymer processing. And so I will just give you the philosophy behind modeling equipment. So our philosophy in developing an understanding of what happens in a mixing equipment, and also perhaps draw some conclusions for process and control and design optimization, is first of all to develop a methodology for modeling mixing in processing equipment. We also want to define rigorous measures of mixing quality to be used as criteria for control and optimization. And finally, we would like also to characterize the dynamics of the microstructure using fractal analysis. And so this is just one slide to show you that we do also some math and we do some simulations, but that's not important. We use finite element method. We solve all those equations. We get flow field profiles. We take into consideration fluid rheology, boundary conditions, and so on. Now, this is more interesting, and I want you to see that we also look at the dynamics of the mixing process. So we put those massless particles in the flow field, and we watch how mixing progresses, how they flow how they advance in the flow field. And so the story is, how can we define those rigorous measures of mixing quality? So for dispersive mixing, which is the process I talked about, which is breaking up the agglomerates, the fine particles, the important characteristics for mixing are the magnitude of the applied shear stress, which is obviously because you want to break the agglomerate, but also the characteristic of the flow field, the flow strengths, how much elongation of flow components you have. And so for that reason, we actually use a parameter, which is the ratio of the magnitude of the rate of deformation tensor to the rate of deformation tensor and vorticity tensor. But the reason why I put that up on the slide is because we were the first research group to use that criteria in trying to control mixing and optimize mixing equipment. And so for that reason, Tim Oswald, who wrote a book on understanding polymer processing, defined a dimensionless parameter, which he called MZ, which pleased very much my husband because M is in capital. So going after what is important for distributive mixing, we thought about the concept of entropy. And so entropy measures the level of order-disorder in a system. And so the higher disorder, the higher the entropy, the better the mixing. So this is also something which was used first time in our research group. Now I want to draw your attention to what is really the benchmark of good mixing. So the benchmark of good mixing is how to make a dough. And we'll ask a baker how you make the dough. So what you do, you actually squeeze and fold, and squeeze and fold. And that's the benchmark of good mixing. Can we apply it to polymer processing? Yes, sure we can. So when you think about, let's say, mixing polymers of two colors, so what we do is here you have the red and the black. You stretch and squeeze, and then you fold. Now we can do better. How can we do better? We can stretch, squeeze, cut, and fold, or stack, okay? And that actually is increasing much more the interface between the red and the black. Therefore, it's a much better way to do mixing. So here in terms, just to make sure that you understand, we actually decrease the striation thickness of the polymer, of the two streams. Now here is the Baker channel, so coming from that Baker transformation. So in the Baker channel, we simulated how to put two streams, one red and one black. And what you want is to increase the interfacial area between the red and the black. But it's also interesting, if you pay attention, you started here with only one line between the red and the black. And if you apply this Baker transformation, you increase the interface between the black and the red. And so we go in various steps from that single line to actually many lines which will fill a surface. So if you think about it, you go from a 1D, which is a line object, to a 2D, which is a surface. And so that suggests a fractal behavior. And so it's exactly because of that fractal behavior that we can actually look at the dynamics of the microstructure through fractal analysis. Now, that brings us to how can we use all this knowledge in new materials for wind turbines. And so the way in which we harness the wind power is by building larger and larger wind turbines. To build all those larger and larger wind turbines, we need materials which will have certain properties. So we need affordable materials with high strength to mass ratio in order to enable those larger wind turbines. And we thought about carbon nanotubes as a way to improve that strength to mass ratio of material used in the wind turbine blades. And so if I should tell you the state of the art, currently what people are using are polyester, vinyl ester, epoxy, usually reinforced with glass fibers or carbon fibers. But what's the key here? The key is to have enough stiffness in the blade, but also to have a long fatigue life, because just think about how much fatigue those blades will endure. And so carbon nanotubes are those wonderful materials which have extraordinary important and good mechanical properties. We thought about putting those carbon nanotubes into our matrices. And yes, that's success. Because just by using carbon nanotubes at 0.3 weight% into the epoxy, we increase the average fatigue life by 1,550%. Now that's remarkable. And so the idea is that those carbon nanotubes can actually make wonders as long as you know how to mix them. Now here are some SEM slides which show the fracture surfaces of those materials. This is just the epoxy, and this is the epoxy with carbon nanotubes. Now you see a much rougher surface, and so that means that it is it's much more resilient, it's much more strong and tough. Now here is just also an example of a carbon nanotubes pulling out of the matrix and deflecting the advancement of the cracks into the material. Okay, so that brings me to about the finish line of my talk. So I would like again to thank the Seitz family for this wonderful opportunity to do more research in this area. And I want to show you that those materials are important not only for the wind turbine blades, but they are important to build better aircraft, or to make better tennis rackets, or to make more efficient cars. So all those composite materials are important not only for harnessing more wind power, but also to make our life better. Which brings me to the final slide, which is acknowledgement. So first of all, I would like to thank Case Western Reserve University for providing me such a great opportunity to develop my professional career. I also would like to thank all my sponsors for giving the money to do all this research. I also should say that I learned a lot from my teachers, and I'm very grateful for that. But I learned more from my collaborators, right there in the front row. But mostly, I learned from my students. And I'm indebted to my students for making my life so wonderful. And this is actually not me only. Our ancestors also wrote the same quote, that I learned much from my teachers, more from my colleagues, and most from my pupils. I also would like to thank you very much, all of you, for coming here today to celebrate that inaugural chair. I'm very much indebted to each and every one of you, to my family, to my friends, to my dear colleagues, to my dear students. Thank you very much.
We're going to keep Ica up here for another minute. We have one last thing to do to make it really official. And to do that, I'm going to ask the Dean of the Case School of Engineering, Jeffrey Dirk, to come up and do the honors.
So we've had a great opportunity here about mixing today, and really the endowed professorship is an opportunity to mix the generosity of a donor, the Seitz family, and the scientific achievements of a faculty member. And I think it's important to remember that endowed chairs began in 1502 when Countess of Richmond and grandfather of future King Henry VIII created the first endowed professorships in divinity at Oxford and Cambridge. So the tradition of endowed professorships goes back really, I think, to a lot of our heritage. But it was only a short time later that private individuals soon began adopting the practice of endowing professorships and creating essentially that tradition and legacy that links a family with the scientific achievements of an institution. And so today we're here not only to celebrate Ica, but also the Seitz family. Lucasian Chair, for example, of mathematics at Cambridge was originally held by Sir Isaac Newton. Today, we celebrate the accomplishments of physicist Stephen Hawking in much the same way that we're giving Ica the opportunity to be the inaugural chair of the Seitz, or the inaugural recipient of the Seitz chair. And we look forward to 350 years from now when we're talking about the next recipient or the future recipients of the Seitz chair. So on behalf of the Seitz family and the Case Western Reserve University, Ica, we'd like to present you the Seitz Chair.
Yep, you got to sit in it. No, actually, we're going to keep you sitting in that. We have a party to celebrate this occasion, and it's waiting for you right outside these doors. And I'm going to ask the Seitz family and Ica, your family, to stay for a few pictures. And Glenn, we got to get you in a picture because we had no idea what a critical role you played in all of this, but I'm delighted that you are here. So if I can keep the people in the front row here for just a few minutes, I promise they'll be right out to celebrate with all of you. Thank you all so much for coming today.